Hello. So, in the last video, I showed you two rules for taking derivatives. First, the power rule, where we learned that the derivative, and I'm going to use this notation from now on, of where b is some coefficient and n is some exponent on x, this is equal to bn times x to the n minus 1, or we decrement the exponent and multiply it times the exponent before we decremented. Alright, but that aside, we also learned about something called the chain rule. To be clear, is basically saying, and it's better to use this other notation, where we use a prime symbol to show a derivative, this dash here, that's just what I'm going to be using. It's the same as this, but it can be easily used with functions, especially in that terminology. That the derivative, or f prime, of a function of x, so we're taking the derivative of this whole thing, would be equal to, where g is a function and f is a function, is equal to, it's a bit easier to write with the other notation now that I see it, but it's equal to f prime of g of x, where g of x is basically x. We're treating g of x as x, so I'm going to convert this into x here, but that's actually g of x, right? The function of g of x, and it would be easier if we wrote g of x, but then that would be confusing because we write the same things twice, times the derivative of this inner function, g, with respect to real x. So this is our fake x, which is actually g of x, where we're pretending g of x is just the function of x. We're taking the derivative, pretending that this is g of x, or the derivative with respect to g of x, a small change in g of x instead of a small change in x, times the normal derivative with respect to x of g of x. And when you write it out, it's a little bit less intuitive, but I'm going to give an example. Let's take the cosine squared of x as our f of x. This is a function that we'll be differentiating. Now, this isn't immediately clear. We found out what the derivative of cosine of x is, but what's the derivative of cosine squared of x? Well, we can easily simplify this to cosine of x squared, and now we can use a power rule, because this squared out here is the outer function, like the shell, of this inner function, cosine of x. Now, so if we're pretending this is x, just like we did in the formula, what's x squared, the derivative of x squared? Well, that's 2x. So let's pretend this is x here. We're pretending this is x, so that is 2x, where this is our red x, you could say, the one that we're pretending, or we could use a u, another letter, but this is clear for now, times, now we ignore the outer function, the shell here, the derivative of the cosine of x, which is negative sine of our normal x. And now we can simplify this by putting what x really is back in, and that is 2 times the cosine of x times, we'll just carry the negative out here, but I'll write it here for now, sine of x, or that'll do. And that's our derivative of cosine squared of x. Let's see, did I do anything wrong? Nope. Alright, well that's a pretty clear one. We just have two simple derivatives to take, just a square and the cosine. Now what if we have something a little bit trickier? What if we have f of x is equal to 2 to the x? Alright, this one's a little bit weirder, but we can use a logarithmic property to simplify it a little bit. Now, this is the same as e, the base of the natural logarithm, to the natural log of 2 to the x, right? Because if e is raised to what e is raised to get to 2 of x, then it's just 2 of x. That's the same thing. Now this is a little bit easier to take the derivative of with the chain rule. So what did we learn? We learned that the derivative with respect to x of e to the x is equal to e to the x. And there can be a constant in here because, as we know, derivatives don't care about constants. They just basically delete them because we're only caring about the rate of change, not where it is, so to speak, or the y-intercept. So, using that, we can pretend that this up here, this part here, is our fake x. Right? And just as easily, to simplify things, we can rewrite this all as e to the, if we raise a logarithm to a power, it's the same as multiplying that logarithm by the value of that power. Because of how a logarithm is a power already, if you raise a power to a power, you're just multiplying them. X, natural log of x, natural log of 2, I'm sorry. So the natural log of 2 times x, we treat this as our x, so we're going to treat this as x. So this is our x that we're pretending it to be, and this is what we do in the chain rule. We only care about the outer function, e to the whatever, our inner function. So we're taking the derivative with the respect to the inner function. We just get e to the x, right? But we have to multiply e to the x, which we substituted for this inner function, times this inner function with respect to x. Well, this is the natural log of 2 times x to the first. And just using the power rule, we know that coefficient on x doesn't matter when we take the derivative. We can just take it out of the derivative and put it back in later. So that's the derivative of x times the natural log of 2. The derivative of x, as we learned, is just 1. So it's 1 times x to the 0th power is 1 times 1. So that just gets us to the derivative of this inner function is just the natural log of 2, right? And now we can substitute back in for our x. What is this? Is equal to, alright, e to the, let's put this back in because we want to simplify, natural log of 2 to the x, because, you know, we're not, when we actually simplify this, we can't have the x as being multiplied by 2 because that's, that would be cheating and doesn't actually make sense. It only makes sense if we keep it in a logarithmic form. And now we have e to the natural log of 2 to the x times the natural log of 2. And these simplify. I'm going to use my canceling marker, wherever it is. This one will do. E to the power that e goes to get to 2 to the x. So if you take the power that it has to go to go to 2 to the x, and you raise e to the power of that power, it's going to be 2 to the x. So in the end, this will be equal to 2 to the x times the natural log of 2. And that's our derivative. Alright, so hopefully we have some understanding of the chain rule. Maybe not how it's used or how it works yet, but we do have an idea of how to use it, and that it can be used to take derivatives. So next, I'm going to introduce you to two rules actually, but they're basically one and the same, and so I won't delve too deep into the second one. Now this next one, is called the product rule. And as you can guess, it has something to do with multiplication. going to change markers, keep things interesting. Now, this is used when we need to take the derivative, dx, this marker's kind of wearing out, of f of x, not f of g of x, but times g of x. So when we're multiplying two functions together. And it has been found that we can work through this by using the product rule, and we find that this is equal to f prime of x, so the derivative of the first function with respect to x, times normal g of x, plus, we're not multiplying by, and this is kind of unintuitive, f of x times g prime of x. And the marker is starting to wear out, so I might switch again. Alright, now this is all fine, but we need an example, right? So I'm going to leave that there actually, so that we can look back on it. So what if we have the derivative with respect to x of cosine of x times, well, here's an easy one, e to the x. We might as well get used to e to the x. Alright, so we take the derivative of the first function with respect to x first, and multiply it times the normal next function. So the derivative of cosine of x is negative sine of x. And then we multiply times the second function, e to the x. I'm going to put it in parentheses because it would look kind of weird signing x e to the x. It would look weird. And then we add the normal first function times the derivative of the second function. And lucky for us, the derivative of the second function is itself. So plus cosine of x times e to the x. And we're done. That's how we do it. This can be used in a lot of different methods and is will be very important later on and in your career in differential calculus.